If you want to master the physics of the human eye and the colorful world around us in under 5 minutes, you don't need to memorize a textbook. You just need to follow the unbroken journey of a single photon, starting in the black vacuum of space and crashing right into the glowing blue edge of Earth's atmosphere. Take a look at this animated diagram of our atmosphere. It's not one uniform block of air. It's a stack of distinct layers, each with varying temperatures and densities. As light penetrates from a thinner, rarer medium into a denser one, its speed changes, causing the ray to continuously bend. This is atmospheric refraction. Still looking at the diagram, watch what happens to the light from a distant point source, like a star. Because the atmospheric layers above us are constantly swirling and rippling, the refractive index shifts every millisecond. The angle of the light fluctuates before it reaches your eye, causing the star's apparent position and brightness to flicker. We perceive that as twinkling. Planets, on the other hand, don't twinkle. Because they sit much closer to Earth, they act as extended sources, essentially a collection of many point sources grouped together. The slight flickering from all those different points averages out, leaving a steady beam of light. This continuous bending of light also alters our perception of the day itself. When the sun is physically just below the horizon, the atmosphere refracts its light downward. This optical trick makes the sun visible about 2 minutes before actual sunrise, and keeps it visible 2 minutes after actual sunset, granting us 4 extra minutes of daylight. Everything we observe in the sky, from the flickering of distant stars to the position of the sun, is an optical illusion dictated entirely by the continuous shifting density of the invisible air above us. As our photon descends into the lower atmosphere, it starts hitting physical obstacles, suspended particles of dust, smoke, and water. When light collides with these particles and scatters in different directions, it creates what physicists call the Tyndall effect. This diagram demonstrates exactly why our sky is blue. When white sunlight strikes a fine atmospheric particle, the short, tightly packed frequencies of blue light scatter aggressively in all directions, dominating our field of view. Now watch how a long, wide red wave behaves. It smoothly bypasses those exact same particles without scattering, traveling in a straight line directly to the observer. This proves exactly why brake lights and danger signs are painted red. They slice through fog and smoke without losing their focus. The colors we see aren't inherent properties of the objects themselves. They are the result of a physical filter dictating which exact wavelengths survive the journey to our eyes. Let's bring our photon all the way down to Earth and have it strike a solid object sitting on a desk, a triangular glass prism. In this diagram, incident ray PQ enters denser glass, bending toward the normal to establish angle of incidence I. Leaving the glass, it creates emergent ray MR. Tracing MR backward reveals the angle of deviation, delta, measuring the light's total course alteration. Inside the glass, the varying refractive index splits the incoming white light into the 7 colors of the visible spectrum, a process called dispersion. The violet path bends sharply, while the red path has a shallower deviation. Violet bends the most, and red the least. A simple piece of shaped glass demonstrates that what we perceive as a solid beam of white light is actually a composite of distinct wavelengths. After dispersing through the prism, those wavelengths finally reach their destination, the human eye. This schematic maps the entry pathway. Refraction happens at the cornea. Light passes through the aqueous humor to the pupil. The surrounding iris regulates pupil size. Next, ciliary muscles flex the lens to focus light across the vitreous humor onto the retina. Human vision is not magic. It relies entirely on localized biological applications of the exact same refractive physics we just observed out in the atmosphere and inside the glass prism. But what happens to our perception of reality when the dimensions of this biological camera fail? In myopia, the elongated eye causes light to converge too early, missing the back wall. Dropping a concave lens in front diverges incoming rays, pushing the focal point backward to perfectly land the image onto the retina. In hypermetropia, the eyeball is too short, causing rays to converge past the back wall. Dropping in a convex lens sharply bends the rays inward, applying positive power to focus earlier and perfectly hit the retina. Add in presbyopia. the natural, age-related stiffening of the lens and weakening of the ciliary muscles, and you understand exactly why many older adults require bifocals to artificially compensate for that loss of biological flexibility. From the vacuum of space, through the atmosphere, and into the optic nerve, the same rules of refraction dictate every step. This journey connects the flickering